The first speaker of the session is Junghwan from Concordance. He's talk about concordance and satellite operation.
Thank you. Thanks for the introduction. Thanks for the opportunity. So I went to the website and this says, this workshop concentrates on convex real projective structures and overflows with ends hitching components of surface groups. So this talk has nothing to do with that. And I don't know most of the words in here. So I assume that, so I study knot concordance. So I'm assuming a lot of people may not be so familiar with knot concordance. So this is a mild introductory talk on theory of knots and its concordance. So I'll tell you what they are. And I would like to tell you some open problems that I find interesting. And I will tell you a little bit about why people care about knot concordance in general. So let's start with the objects. Knot is a smooth embedding of a circle inside S3. So there are a bunch of examples. This one is the simplest possible one, the unknot. So we call this the unknot. The next one is slightly more complicated. This one's called the trefoil. This one's called the figure 8. I think because you see this 8 shape, this one maybe it's called figure 8. I'm not really sure. So this one's called the figure 8. And as you can see, knots can become quite complicated very fast. So among these knots, the simplest one, the unknot, has this very special property that it bounds a smoothly embedded disk inside S3. So we'll, and it turns out this is the only knot that has this property. There's only one knot that bounds smoothly embedded disk inside S3. So I would like to upgrade this notion, just replacing S3 with B4. And whenever this happens, I'm going to call that knot a slice knot. Okay, so this is the definition of a slice. And whenever someone says, I study knot concordance, that means that that person is interested in determining whether this knot is sliced or not. So the question that I'm interested in is, can we determine, or should I say, which knots are sliced? So this is the main question that I'm interested in. So first, I'll give you some examples of knot that bounds an embedded disk in B4. So you start with any knot that you like. You draw its mirror image to the right. So you can draw something that looks like this. Okay, and you connect them in the most obvious way, called connected sum. It turns out whenever you do this process, start with a knot, draw its mirror, connect them in this most obvious way, this is always a slice knot. The reason being is that think about for R3, you can think of R3 as there's an axis and there's an R2 plane. You rotate R2 plane to get R3 plus, let's say. You can do the exact same thing with one dimension high. So think of there's R2 axis, there's R3 plus, let's write it as R3 plus plane. You rotate R3 plus plane, so they will make R4 plus. And if you keep trajectory of this arc, this trajectory of the arc will draw a smoothly embedded disk inside this four manifold, where the boundary is this knot over here. So we often write this part as minus k, where the mirror image. So this says that for any knot, k connect sum, its mirror is always slice. So maybe this sounds a little artificial, but in fact, there are many more knots which bound smoothly embedded disks. I'll give you another concrete example. So this is what I was afraid of being recorded. So I shamelessly copied a picture from Peter Teichner's lecture note. so if you go to page 2 or something like that, you'll see this picture. So this is what's going to happen. Inside the S3, I'm going to see some move of the knot, and I'm going to think of S3 times interval as S3 times a time coordinate. So you should think of it as you go to the right, time is flowing. So you start with S3 times 0, and as time goes by, you get S3 times 1 over 3, S3 times 2 over 3, and S3 times 1. So inside S3 times I, abstractly, this is happening. You start with a knot that you are interested in. So abstractly, just a circle. Through time from 0 to 1 over 3, nothing much happens. Abstractly, you still have an embedding of circles throughout 0 to 1 over 3. So that's from here to here. But something drastic is going to happen from time 1 over 3 to 2 over 3, which is you look at these two strands, they will get merged and get separated like this. That's exactly the saddle point that you can see at this point, right? So after that, I have two circles, one green and one red. This circle, you can perform a little bit of isotopy. You can easily see that it's isotopic to this two-component link, which goes from 2 over 3 to 1. Once you are at the stage of two-component unlink, you see that there's a smoothly embedded disk. So you just cap that off with B4 below, like this. So this gives you a smoothly embedded disk bounded by this knot, which is called a stevedore knot. So this is an example of a slice. Do we have any questions? Okay, so at this point you might be thinking, okay, is every knot slice, which is not true. Otherwise, we'll be done with our business. It turns out we can find many different non-slice knots. So this goes all the way back to the 60s. The first ever obstruction of not being sliced was invented by Fox and Miller. So what they do is you look at a knot complement. Recall that H1 of the knot complement is Z. So you have infinite cyclic cover of the knot complement. So you look at the infinite cyclic cover and you look at its homology. And you try to extract algebraic information from that. That is often called Alexander polynomial. So what they showed was if you have a slice knot, this algebraic information can be written as a product of two polynomial, ft times ft inverse. So this is actually quite a useful obstruction because the Alexander polynomial is very easy to compute. So for instance, for the trefoil, if you compute it, it looks like this, t squared minus t plus 1. For the figure 8 now, if you compute it, it looks like that. And it's an easy exercise for you to check that this never factors as ft times ft inverse. So this was the first obstruction for sliceness. After this, Jerome Levine, he kind of packaged this to something more general. So he looked at so every knot bounds a cipher surface. From the cipher surface, you can obtain information called the cipher matrix. So collecting all the cipher matrix can give a group structure that is called algebraic concordance group. So in particular, that subsumes this Fox and Miller condition. So he showed that there is this algebraic obstruction called algebraic concordance obstruction. And in fact, that was kind of very interesting because when you look at higher dimensional odd knots, you can still talk about this knot concordance question. In fact, this algebraic concordance group completely determines which odd high dimensional knots are bound the appropriate ball inside appropriate bigger ball. So for higher odd dimensional knot theory, knot concordance theory, this algebraic information was enough. But surprising thing happened in the classical dimension, which was in the 80s. Cass and Gordon used this G signature theorem. And he was able to show that even if you're not satisfied this algebraically vanishing obstruction, there exists a knot which is not smoothly sliced, doesn't bound the disk inside B4. So that was the first very much big breakthrough. After that, there's something called L2 obstruction, which came from Cochran or Teichner. And there's a bunch of gauge theoretic arguments, instantons, Seiberg-Witten, Hagar-Floor, you saw it from Sung-Young's talk yesterday, and even Kavanagh homology. There are many different techniques, which even today are being used to find some obstructions for not bounding a disk inside B4. So Sang-Young's talk, he talked about involutive Hegar-4 yesterday. After my talk, he's going to talk about this Seiberg-Witten floor homotopy type invariant, which is kind of a cutting edge technique, which will be interesting to hear. So what did I want to say at this point? I would like to say, maybe this is a little controversial, but maybe this is not controversial. I wanted to say that this is the first result from the 60s. Now it's been 60 years. So many techniques have been developed. So we became very good at non-slicing knots. There are many techniques. So for instance, if you go to a board, you draw any knot. If it has less than 13 crossing, we, as in a group, we can tell if that knot is sliced or not. So the technique has grown, and we know a lot about knot concordance. Yet, there is this very natural operation called satellite. Somehow, if we perform the satellite operation to knots, we become somehow clueless. There are many open questions that we have no idea how to answer. So my goal today is to introduce some of these problems. And one observation I made a few weeks ago with Jennifer Hom, somehow there is some connection between these conjectures that I didn't know that was true. It seems like you only need a very fundamental ideas to prove this. So I thought it might be appropriate to talk about this in this talk. So I'll tell you what the connections are for those conjectures. So before I get there, maybe I'll give you a little bit more of reason why people might care about study of knot concordance. So why do we care? So the original motivation for Fox and Miller was to understand embedding of surfaces inside four manifolds, allowing singularities. So let's say I have an embedding of a torus with bunch of singularities. So what happens is, so this is inside the four manifold. So if you go to the singular point, if you look at its neighborhood, this is the four ball, B4, is four manifold. So the boundary is S3. So if you take S3 and look at the intersection of S3 and the surface, this is a one-dimensional connected manifold, namely S1. So every singular point, there is a knot there. And whether you can resolve the singularity is exactly the same question as, does this knot bound the smoothly embedded disk inside B4? So in fact, this is related to understanding embeddings of surfaces inside four manifolds. That's one relation. Also, for any knot that you start with, there are many natural stream manifolds which is associated to this. So for instance, there's something called surgery or Dane surgery that you can perform on. So let's say I do 1/n Dane surgery on K. One is just to represent that this is a homogeneous three-sphere. H1 is equal to 0, and can be any integer. So every n, you might spit out different string manifold. And the relation is that if I have a slice knot, this three manifold bounds a contractible four manifold. So in study of dimension 3 and 4, this doesn't happen very often. For any two manifold, you can find the simplest possible filling of that two manifold. For the three manifold, this is kind of rare thing to happen. And a lot of different techniques has been going on, has been developed to understand how to obstruct this kind of phenomenon. So if you can show some three manifold, surgery or not, cannot be filled by a contractible four manifold, you'll be showing that the knot K is not sliced. But it can go other direction as well. If you're interested in finding a very simple filling of the three manifold, you would try to show that knot bounds smoothly embedded disk inside, for instance. So this is one natural connection, or you can perform branch cover as Sang-Young was talking about yesterday. So more generally, you can look at prime fold branch cover. And it turns out this bounds a so more precisely is ZP homology bulk, but let's just write rational homology B4. This just means a four manifold that has the same homology as B4 with Q coefficient. So interesting thing that Sungkyung and I have been doing was that beyond this information, in fact, this is equivariant rational homology B4. Which means that on the boundary, we have this natural deck transformation, natural action on it. This four manifold not only fills, but this action extends to the four manifold as well. So it turns out this is a quite important information that gives you many interesting obstructions. Also, this goes the other way around too. If I want to know if this three manifold bounds equivariant filling, maybe we should look at the knot and see if that knot bounds the disk inside B. Okay. So these kind of things that we like to study. More generally, any three manifold can be obtained by surgery on some lengths. For the lengths, you can also study concordance of lengths. So there are many close connection between study of link concordance and study of homology cobordisms and which three manifold bounds what kind of four manifolds and stuff like that. So this will be one motivation to study these kind of things. Any questions so far? All right. So satellite construction. So this is what you do. You start with any knot that you want, and then you draw a knot inside a solar torus. So I'm going to draw this knot inside a solar torus. Then what I'm going to do is put the solar torus in the original knot. So it amounts to doing something like this. Okay, very good. So taking a parallel copy, I have a clasp here. So adding a clasp that looks like this. Okay. So this is a satellite construction. You start with any knot you want, and also some knot inside a solar torus, which is called a pattern usually. And if you have these two combinations, it can always spit out a new knot. So this pattern is quite widely studied, plays an important role. So this has a special name. It's called a Whitehead pattern. So this knot is called Whitehead of the figure 8 knot. Okay. So the game is put something in the solar torus, take the solar torus, tie it with the original knot. So if you do the same thing with the figure 8 and this pattern over here, I get something that looks like this. So it's just, again, a parallel copy, but I have this kind of half band attached to it. So this is called a cabling operation. And it's 2-1 cable because I took 2 parallel copies. But in general, you can take 4 parallel copies, 6 parallel copies, and so on. So you have e to the 2-1 cabling operation. Inside the solar torus, it doesn't have to be a knot. Sometimes it can be a link, just like in this picture over here. This is called a Bing doubling pattern. So then the resulting thing, I started with a knot, but I will get a 2-component link. So this is called Bing double figure 8. Okay. So from the very simple knot, there are a bunch of these operations to get something still quite simple, but a little bit more complicated than the original knot. So I told you that the Fox and Miller theorem told us that this is not slice. So now you can ask, I take this non-slice knot. If I perform these operations, you can ask what happens, right? So the answer to that is, this is not known. E to the 2-1. Many cases is known, but a lot. So half of the cases known, half of the cases not known. So when n is 2k plus 1, it's not slice. And n is 2k. Wait, this is not known. And this is co-work with Sangyeong and many other authors. Wait, I should remember all their names. Okay, so EKMPS 22 and PT 24. That's right. Dai, Sangyeong, and Abhishek Malik, myself, and Sofragan, and the second one. So this was for 2N cable, and KPT is Sangyeong, me, and Masaki Taniguchi. This was posted recently. And for the being double of E, this was also not resolved for a long time, but it was resolved about 10 years ago by Jechun Cha. So this is not slice. So as you can see from the years 2010, 2022, 24, this was not an easy problem. It took a while to solve these kind of problems. And even this most well-known example, we still don't have any idea how to resolve this question, for instance. So this is kind of surprising for me because if you before doing satellite, we have many good answers to whether the knot is sliced or not. But as soon as you take very simple knot and perform the satellite, many open question just suddenly arises. That's kind of surprising thing to me. That's a great question. I'll come back to that. I think so. So this question over here actually belongs to that. It's a sub question of that general question. So the main motivation is that if you take something which doesn't bound the disk, if you perform this simple operation, there's probably no way to find a new disk for the something that didn't bound the disk, right? So it belongs to that more bigger picture of the question. So let me get back to that. So, but one thing I want to make a remark is that if I start with a slice knot, the resulting any pattern that like at least these patterns, it becomes slice. The reason is that first notice that if you have a slice knot, that bounding a disk inside before is exactly same thing as not co-bounding annulus with the unknot inside S3 times I. So we saw that this knot is slice. That implies that there is an annulus between this and the unknot, just because usually I have this, but you can just take a point and just push it in to downstairs S3, then you can find an annulus. Also, the other direction goes true. So if you have an annulus to the unknot, you can cap it off with a disk. So bounding a disk is same thing as the existence of annulus to the unknot. Now, if you have a annulus to the unknot, what I can do is you consider its tubular neighborhood times I. Inside S1 times D2 times I can plug in this pattern throughout the interval so that pattern times I throughout the interval. So if I glue this S1 times D2 times I to this tubular neighborhood, on the top, I'll be getting Whitehead double of this knot. On the bottom, I'll be getting Whitehead double of the unknot. But Whitehead double of the unknot is the unknot, right? So we already, again, found the annulus between Whitehead double upstairs and Whitehead double of the unknot, which is the unknot downstairs. So one thing to note is that if you have a slice knot, any of these operations will spit out slice knot. And the expectation is that this is the only time when you'll get slice knot. Whenever you have non-slice, it spits out non-slice. When it's slice, it will spit out slice. So all of these problems belong to the questions that you were asking. So this belongs to the conjecture. This is a well-known conjecture that says K is slice if and only if y of K is slice. So this belongs to, again, K is slice if and only if K of 2 and 1 is slice. Conjecture 3, let's say K is slice if and only if Bing double K is slice. And we are just trying to find more evidence to this particular question over here. And this question was around for quite a long time, especially this question is most well known. So let me show you this. So I don't think this is so we see in our field we have Kirby's list. So it's like a collection of open problems that so now there are three, like third version now. The first version was made in the 70s. It was updated in the 90s. Now people are working on updating for the last version. So it was stated in the 70s. The double of knot is sliced if and only if the knot is sliced. That's the conjecture one that I was talking about. It's still stated as 1.38. But the reason I pulled this up is that there's this word unlikely here, which I find kind of interesting. I don't know what people would say about this conjecture these days, but at least in the 90s, people thought this may be unlikely. And they say the conjecture are improving, the odds of the conjecture are improving because the Rudolph showed that y-det double of trefoil is not sliced, or more generally y-det double of positive knots are not sliced. So since then, again, various different techniques from gauge theory and many different techniques have been applied to show y-det double of many knots are not sliced, but still, like for instance, we don't know that this is sliced, or y-det double of left-hand trefoil sliced. We don't really know. So it's far from resolving this conjecture. Anyway, so I wanted to introduce these problems to you today. Are there any questions? Yes?
Just the 2N cube thing.
Right. So that's right. So for the argument that I made for this to work, what did I use? I used the fact that when I do it to the unknot, it is the unknot. So if you do PQ cable of the unknot, it's a torus knot. So you should do P1 cable, but you can also think about odd one cable in general as well. Yeah, also Song and I considered odd one cables a while ago. Yeah, but for the purpose of this talk, I only covered even one cable. Great. Any other questions? Okay. So I knew about these conjectures, and I knew about another conjecture which is kind of similar flavor, but it looks quite different. And I was talking to Jennifer Hom a few weeks ago, and at least it was surprising for me that the conjecture that I'm about to tell you about has some relation to this conjecture. So I thought it might be interesting to share this with you because the argument is very fundamental. So I think maybe the experts already knew about this, but I think maybe suitable for talking about this in this conference. So the related conjecture is called, I'm not sure if it has a name, but let me just call it parallel link conjecture. So what is it? So so let me tell you the setup a little bit. So apparently the 70s, so this was before my time, people were curious about if every link can be changed into the split link up to concordance. So what is a split link? Link is split if I can separate them in a separating two sphere. So if you can find a ball and there's an outside ball. If I can put one knot inside one ball and one knot inside the other ball, those are called split links. So if every link can be changed into split link up to concordance, that means that link concordance essentially is just study of knot concordance, right? So there's no reason to consider more complicated things because everything can be separated into each of the component knots. So this was asked in the 70s. In the classical dimension, this is very easily proven to be false. There's a notion of linking number, and there's also a notion of Miller's invariant, which is invariant under concordance. So examples like this, half-link or Bromian rings, they have non-trivial invariant linking number and Miller's invariant, which implies it can't be splitted up. But in higher dimension, it's more complicated. And the answer was given by Capel-Shanison in the 80s and separately by Kawauchi in the 80s. So they come up with infinitely many examples of links, higher dimensional links, which can't be simplified to split link, even up to concordance. And for even dimension, apparently it's not known. For even dimensional knot concordance, for knots, we understand it very well. Everything bounds appropriate ball, but for links, this seems like a very difficult question that I don't really know the answer to. But I bring this up because I want to focus on what Kawauchi did in the 80s. So what did he do? He considered something called parallel links. So it's exactly what you think it is. You start with a knot, you just take a parallel copy. So this is an example. Okay, so take a knot, just take a parallel copy. I took a two parallel copy, so I'm going to call this E20. Okay, so this is what he proved. In higher odd dimensions, he proved that K20 is concordant to split link if and only if K is slice. The argument that I showed you earlier implies this direction. So his main contribution is to show the opposite for higher dimensions. The classical dimension, as we saw, this is an easy direction. And he leaves this as a question. Is this true? So let me call this a parallel link conjecture. So the question is that if I know that parallel link is concordant to split, does that imply my knot has to be sliced to begin with? Okay. He leaves this as a question and he says, I know how to show that for the figure 8 knot, if you do 2-0, it doesn't split as a parallel link. But in general, he says he doesn't know how to take care of this. So it seems like, I don't know, at a glance, this conjecture doesn't really seem like related to the conjecture 1, 2, 3 that I talked about earlier. But apparently, this is true. So maybe I should write Jen's name. H, P. Okay, and P. Maybe 24. I don't know. So what we can show is that if the parallel link conjecture is false, then all three conjectures are false. More precisely, if you can find a knot which is concordant to a split link, then for that knot, whitehead double is slice, 2n1 is slice, and Bing double of K is slice. And moreover, for Bing double case, we can show if and only if statement as well. But it's slightly tricky. For the 4 manifold, it's not actually B4. It's a rational homology B4. But to be more precise, it's Z2 homology B4. But there's a converse statement that you can make for different type of 4 manifold. So this is a little surprising for me, but I think maybe experts already knew. I'm not sure, but the argument is completely fundamental and elementary. So I would like to share this with you today. Any questions about the statement? So for the simplicity of today's talk, I'm lying a little bit. So in reality, when you have a knot, you have to choose an arrow, direction, orientation. Either you choose this direction or this direction. Sometimes they give you the same knot. Sometimes they're not the same. When they're the same, we call the knots are reversible, but not all knots are reversible. But let's assume today that all knots are reversible. I think that's okay because every knot that we've seen so far today, they're all reversible. Okay, so let's just pretend orientation of the knot doesn't matter just for today's talk. Okay, so let's prove the theorem. So I'm going to start with a lemma that says if the parallel link can be simplified to a split link, then first, each component can be made to be k and k. Second, connect sum of these two knots are actually sliced. So let's see how we can prove this. So assumption tells us that this parallel link can be turned into the split link J1 and J2 inside S3 times I, right? I have this annulus A1. I have this annulus A2. Let's reuse this annulus to turn this into K and to turn this into K like this, and they're still split. And again, I'm just concatenating S3 times I from top to bottom, which again gives me S3 times I. So I start with a parallel link. Now I have K and K like this. So that's the first statement follows easily. For the second statement, okay, so I need to draw a cartoon picture of S3 times I. So let's do this. So let's think about this as S3, okay? This is S3. Let's think about S3 times I. This means I have a smaller sphere inside. And here is filled in, right? So I have S3 times I. I've shown that K20 is concordant to split link with K disjoint union K. So let's put the concordance here. So I have K20 is concordant to K here, and disjoint union of K here like this. So I have S3 times I have a two disjoint annuli inside S3 times I bounded by 20 and K disjoint union K. Okay. What do I know about K disjoint union K? They're separated by separating two sphere. So let's draw a separating two sphere. Like this. So inside this imaginary B4, the separating two sphere bounds B3, right? So now let's take a slight neighborhood of this. So you can consider S2 times I and B3 times I, like this. Okay. So what is this four manifold? So think about as the whole big B4, and I took out this ball out and this ball out. So far I have B4 minus, let's call it B1, B2. Okay, this is a four manifold that I have right now. Are we happy until here? So now what I'm going to do is I'm going to cap off B4 from outside. So outside I have S3 as a boundary. S3 bounds B4, I'm going to cap it off. So what is this? In fact, this is S4, and I took out B1 and B2 out. So what is this? If I have a S4, if I take out two balls out, some of my students should be able to answer this. That's right, S3 times I, right? So if I have S4, if I take out a ball, it's it's B4. If I take out a ball outside of B4 again, it's just S3 times I, right? So this union B4 is just S3 times I, okay? Inside this S3 times I have two annuli. I start with here, goes all the way to one of this component. But in fact, for the parallel copy, I can connect these two annuli using this annulus that we see. So annulus, annulus, and then another annulus coming back to here. Does that make sense? I have annulus. At the end of the annulus, I have another annulus, and that annulus is connected to end of the annulus is again connected to a knot with the annulus. So I started with a K. Inside S3 times I found this annulus that starts with K. In the end, what I get is a minus K because I'm looking at from the other side. So I get a minus K like this. So if I want to summarize what happened, that picture over there shows you that inside S3 times I, there exists the annulus from K to minus K. Annulus could be complicated, but I have a smoothly embedded annulus inside S3 times I. So what's the upshot? Upshot is that inside this annulus, I can find an arc that looks like this. And since we are in dimension 4, arc like this can be isotoped to just point times I. This is a trivial arc. So when you perform this isotopy, you can upgrade this to ambient isotopy. So if I look at tubular neighborhood of this arc, which is just, for each point, it's just going to be B3 times the interval. So I have S3 times I, and I can look at its complement like this. But since this arc is trivial, each stage I have S3 minus B3, S3 minus B3, S3 minus B all the way down, which is just B3 times I. So if I do this, I get B3 times I, which is just the 4-ball, right? Which means the boundary of this is just S3. Okay. So let's see what happened to this annulus. I have S1 times I, but when I carve out this ball, each S1, I'm removing an arc every time as I go down the interval. So what happens to the S1 times I? This turns into I times I, which is just B2, right? So now let's think about what the boundary is. Boundary of the arc, I times I. So I still have this portion. So let's draw it like this. And then when you follow this B3 times I have these 2 points that intersects the ball, and it goes down and down and down, right? So that 2 points are just going to be these 2 trivial arcs. In the end, I have, so now we have to be a little careful. So we are looking at from the upside was minus K. So if you look from the other side, it's going to be K again. So I'll be getting K like this. Okay, so we've seen that this knot over here, which is K connects some K, bounds this embedded disk inside B4, which was the definition of slice knot. Okay, or are you more or less happy with the proof? Any questions? But this is like the classical thing. So we have this book called Wolfson. So whoever does knot theory, this is the first book that you read. It's in there. So it's like nothing complicated is really going on here. So that's the proof of this. So I'm not going to go through all the conjectures, but I'm just going to look at conjecture one, for instance. So I'll look at why this would imply why that K is slice. So this assumption gives us that 2 parallel copy is concordant to K disjoint union with K. I'm going to turn this 2-component link into a knot. How do I do this? I just attach a single band that connects one component to the other. So what I'm going to do is I'm going to start here and go to here. I'm going to attach a band that looks like this. Okay, so on the top, I'll be getting a 1-component knot that looks like this. Okay, so what happened? At time is equal to 0, I have 2-component link. Time 1 over 1 or 2, I still have 2-component link. And from 1 over 2 to 1, I'm going to do this drastic change where one moves and get merged to the other component. So inside S3 times I really have this pair of pants co-bounded by whitehead double of K and K disjoint union of K. Okay? So let's take this pair of pants and go back to that S3 times I picture. So I have a whitehead double of K on the outside. I have a K disjoint union of K. Just like before, attach B3 times I. Like this. So again, now this is B4 minus 2 balls. Inside these 2 balls, I'm going to start here. Again, follow this arc and carve out the B3 times I. Just like from the previous reason, this arc is trivial. So this, again, gives me S3 times I. And inside this S3 times I, now I'm seeing an annulus co-bounded by whitehead double of K and is K connexum of K. But what did I tell you? I told you the K connexum K is slice. So this is concordance from here to a slice knot. You can concatenate the annulus to the unknot, which will imply that whitehead double of K is slice. So this kind of things can be proved with this kind of a very fundamental arguments. All right, so that's everything that I prepared for today. Thanks for your time.